Okay, physics, we're going to pick up where we left off on isotopes with atomic excitement. So the first thing is when we drew those Bohr-Rutherford diagrams, remember they were the circle with your nucleus and whatever you had in your nucleus. Maybe you had a P positive and an N0, and then you had an electron floating out here. So there are different shells, and this is going back to your chemistry. So in the first shell of an electron, of an atom, there are 2 electrons. So you can have 2 electrons on that shell. The next shell out, and pretty much every shell out for a little while, we'll talk about that in more detail later, is 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then the next shell out also has 8. That's as far as we're going to worry about for now, is these first 3 shells. So 2, 8, 8. We call this their ground state. And let me see if I can't erase some of this, get it out of the way. Maybe not. All right, so their ground state is that we fill the lower shells first. So you'd fill that shell with 2, then you'd fill the next shell with 8, and once you've used all those up, so that'd be 10, only then do you go on to the third shell and so far. But what happens when the atom is put into an excited state? Well, that gets a little different. In an excited state, the electron is going to have more energy, which allows it to move to a higher energy level. So the atom's can only return to its ground state by emitting energy, which was what we call a photon. So what that means is if we have a an atom with an electron, that's a laser pointer, not a pen. Let's say we're going to keep it simple. We're looking at our first shell. Okay? In an excited state, what you'll have is one of those electrons will jump out to the next shell out. All right? The only way it can return back to its ground state is having energy also. And my pen has died, so I'm writing with my finger. I apologize for the poor handwriting. Is that energy which comes in the form of a photon. So it releases some energy. I don't know why I did that little funky line thing. That energy allows that electron to move back down to its original shell. So let's draw the excited versions of some of these isotopes. So here we've got hydrogen. All right, hydrogen 2, that's the excited version. You can see that one electron has jumped out to the next shell out. Carbon would normally have carbon 14 would normally have, you've got 2 in that first shell, and then would have 4. 1, 2, 3. This electron here has jumped from the second shell out to the third shell. Okay? Just like you can see this one here has jumped from the first shell to the second shell. And chlorine. So we're looking at 1, 2 in the first shell, 1, 2, 3, 4, 5, 6, 7, 8 in the second shell. And in that third shell, 1, 2, 3, 4, 5, 6, that 7th one has jumped into the outer shell. So radioisotopes, these are isotopes that they aren't stable. So they're going to emit radiation in order to help them change their nuclear structure to become a stable atom. So radiation is harmful if safety measures are not in place. So if you think about an X-ray, what do? They cover whatever part of your body they're not X-raying in a lead blanket. And they get that machine really close to your body so it's not spraying out in different directions. People that work in X-ray, there's actually lead in that wall that they go behind when they go to hit the button. to protect them. There are certain radioisotopes that benefit society. For example, X-rays. Okay? Here are some, radiation. X-rays is radiation. Here are some of the isotopes specifically that we use kind of on a daily basis. So americium-241, they put that in smoke detectors. That radiation that it's giving off is what's going to trigger us to notice when there's smoke in the air. Phosphorus-32, they'll put that tracer into plants to track the phosphorus used in plants. That allows people to be able to tell if there's enough phosphorus in the plants or which plants are using phosphorus, so they know to add it to the fertilizer. Cobalt-60, this is used in food irradiation to make sure your food's safe to eat or to sterilize medical equipment. Obviously, those are in two different formulas. Carbon-14, we use that to date how old something is in archaeology. Technetium-99, that's in medical imaging. So that's one that you'll see a lot in different types of X-rays, nuclear medicine, CAT scans. Iodine-131 is medical diagnosis and treatment. That is one of the types of that you might maybe drink or they might inject into you, so when they do a medical test, they can see what you're seeing, or what might be going on in your body. I think we've talked about that a little bit. And the treatment, I believe that one can be used in like radiation therapy in chemo or cancer treatment. Cesium-137 sterilizes insects. Why would we want to sterilize an insect? Well, if we have an overpopulation of an invasive type of insect or one that's carrying diseases, if we sterilize them, they don't reproduce and then they don't spread that disease. Okay. Generally, we think of radiation as, danger, Chernobyl, right? So it's generally we have a poor opinion. But it's used in a lot of different ways when done safely and in line with scientific methods. It can save a lot of people's lives, not just from medical diagnoses, but like we were talking about, sterilizing equipment, making sure your food doesn't have any radiation, or cleaning or killing different bacteria or stuff in your food. All right? So what do you guys think? Can you think of different ways a radioisotope could be used to keep you safe? We'll talk about that next time we meet in person. And then also write down any questions you guys have for me. You can send them to me, or we can talk about it when we are back in class.